Alright, video number 2, we're going to talk about radiation. So in the first video I spoke about conduction and convection and how conduction is how heat moves between solids or through a solid. Convection is how heat moves through a fluid, so a gas or a liquid. And both of those two methods involve movement of particles. In conduction, the particles are passing on a vibration, but actually not physically shifting position. They're just sort of vibrating around a common position. And in convection, the particles are actually moving en masse, so they're all moving together. Radiation is a bit different because it occurs in air, but it can also occur through a vacuum. So it doesn't just occur in a vacuum. It can occur in air. It doesn't have to be in a vacuum, but it's the only heat method, or the only method of heat transfer that can occur in a vacuum because it doesn't involve any particles. So when we use the term radiation, what we're really referring to is electromagnetic radiation, and we'll talk a bit more about that a little bit later. And this diagram here shows the electromagnetic spectrum, which once again we'll talk about another time. But it shows us all the different types of electromagnetic radiation. We are actually already familiar with one, which is visible light, because we use this one all the time. If you've had an X-ray before, then you would have been exposed to these ones. When you're outside, you're exposed to ultraviolet. When you shove your food in the microwave, you're subject to microwaves. Radiation that we feel as heat very typically is infrared, although sometimes we can also in a funny kind of way feel it as ultraviolet. Ultraviolet radiation, if you've been outside like for a while on a hot day, obviously you get burned, but sometimes you actually don't feel it as heat, but you feel like a burning sensation. Infrared though, you would definitely sort of be going, okay, I'm burning and I can feel a temperature difference. So this is the electromagnetic spectrum. And all electromagnetic radiation travels at the speed of light, okay, which is 3 by 10 to the 8 meters per second, which is as fast as you can possibly go. So X-rays, ultraviolet, visible, infrared, microwave, and radio waves, they all travel at the speed of light because they're all electromagnetic radiation. And when you heat something up, when you heat up a material, yes, conduction and convection will begin to occur, but as soon as your object if it has any heat energy at all, it will be emitting radiation. Now, radiation, or electromagnetic radiation, comes from all of the electrons. So, for example, in a bar of metal, and this will occur in other materials as well. Yes, we are heating up all those big positively charged ions in a metal, but we're also making the electrons move and accelerate themselves as well. If you have an electron and it accelerates, it will begin to emit radiation. And because in a metal, for example, we are accelerating lots of electrons and they're all being accelerated slightly differently, they will all give off a slightly different frequency or different wavelength of radiation. And we'll talk about frequency and wavelength another time. But that's where this radiation comes from. And we can estimate how much energy is being emitted by examining the frequency and the wavelength of the radiation. And we can get a fairly good read on what that is by looking at what's the temperature and what's the color of our heated material. Now this works obviously best with metals, but if we heat up a bar of metal till it's red hot, and I suppose you would stick your hand near it, you would feel some radiation coming off there. Red hot is actually the coolest. Yellow hot is hotter than this. And if you heat something up so that it's white hot, well, that's about as hot as you can go. You can actually reach a thing called blue hot. And after that, you wouldn't actually be able to see the radiation that's being given off. It would pass outside of the visible range. So anything that's above absolute zero is going to give off some radiation, and if we know roughly what temperature is, or if we know what color is, then we can work to either, so the color and the wavelength are related. Yes, the color and wavelength are related. And so, for example, like red is about 700 nanometers in length. We'll talk about this another time. But the wavelength is also related to the temperature of the material. And we make use of this when we're examining stars. So we know that red stars are a lot cooler than blue stars. And because we know their color and we can deduce a wavelength from this, this gives us an idea of, well, how hot is the star? What temperature, what's the surface temperature of the star? And then from that we can get lots of other bits and pieces of information. When you heat something up, okay, as you can see, as the object gets hotter, the range, this is the range of wavelengths that it's given off, or it's giving off. As we heat it up, we can see that the range, yeah, it's still fairly large, but the wavelength that we're interested in is this peak one here. This is the one that is given off the most. And so, very typically, as you heat up a material, the wavelength of radiation that it gives off decreases. Okay, so the hotter the object, the shorter the wavelength of radiation. And we denote wavelength by this funny symbol here, which is lambda, which kind of looks like a backwards H. And Mr. Wien, who was a scientist many, many moons ago, he was able to come up with, well, there's a relationship between this peak wavelength and there is also, so between the peak wavelength and the surface temperature of the item that we're having a look at. And if we know the peak wavelength, which is in meters, or if we know the surface temperature, which must be in Kelvin, not degrees Celsius, it must be in Kelvin, then if we multiply these two numbers together, he found that he somehow always generated this same constant number. So we call this constant Wien's constant, which is 2.898 by 10 to the minus 3 meters Kelvin. And if we know this constant, and for example, we know what the peak wavelength that is being emitted by a hot object is, then we can get a fairly good approximation of what is the surface temperature of that material. Okay, so this is Wien's law. And we'll need to be able to use this law as we go along. So it's the peak wavelength multiplied by the surface temperature in Kelvin, and this gives us some sort of a constant. And we can see down here, for example, that here's a red star, a yellow star, and a blue star, and we can say this is the visible range. And we can see that a red star, most of its radiation is emitted, the peak is in the red, that's why it looks red. A yellow looking star, the peak is right in the middle, so we see it as yellow. A blue star, the peak is actually outside the visible range, but within the visible range, the highest sort of point is the purple and the blue, so we tend to see the star as blue. So the hotter the object, the shorter the wavelength. Now we can make use of the fact that different objects give off different amounts of radiation, and we can use like a thermal imaging camera to see lots of different things. So the military would make use of thermal imaging cameras to try and see if there are any bad guys within a building. But we can also use thermal imaging for insulation. I actually think the school is currently they're getting a thermographic analysis of all the buildings. So someone is coming around Westbourne very soon with a thermal imaging camera to see where is the heat being lost in all the buildings. Because if we can reduce the heat loss, we can reduce our energy costs. We can see here that this house is not losing a great deal of heat energy because the outside is very cool. We can see the windows are a little bit warmer because we've got more heat transfer coming through here. This side of the building, maybe it doesn't have any insulation, but we can see that it's much hotter on the outside, which means that more energy must be escaping. So this is making use of the radiation that we can detect. And we can see, okay, this half of the house is pretty bad. This half of the house is pretty good. This is what a human body looks like under a thermal imaging camera. We can see that our skin, and in particular our head, gives off a lot of radiation because they're very warm, whereas closed show up as a bit cooler. And some of the terms that we use to describe what radiation does as it is emitted. So once it's emitted or given off, that radiation might strike a surface and then it might do something. So when radiation strikes a surface, it can be either transmitted, so which means it can pass through something. So things that are transparent or translucent, which I'll show in a second, radiation can pass through these, so it is transmitted. It might be absorbed, which means it's captured. So when it strikes the surface, the energy is captured by the material. So black or matte surfaces or very rough surfaces are very good at absorbing heat. Very light coloured or white or very shiny surfaces are very poor at absorbing heat. Shiny surfaces or white surfaces are very good at reflecting heat. They make the heat bounce off, or the radiation bounce off the surface. Hence why, for example, the things you put on your windscreen on a hot day to keep the sun out or keep the heat out, big reflective surface because it reflects the heat out without actually absorbing any of it. So radiation can be completely or partially transmitted, absorbed, or reflected. And these three things don't happen just in isolation. So when heat passes through, or when radiation passes through a window, most of it will be transmitted, and a little bit will be absorbed, and a little bit will be reflected. And when we're talking about transmission and absorption, this is transparent, that's translucent, this is opaque, so not see-through. Absorption, black absorbs more heat than white. And a space blanket or an emergency blanket is silvery coloured, not to reflect the heat on the outside, but to reflect any of the body heat of someone sort of caught out in the cold, any of their remaining body heat. We don't want it to escape. So you put a very light silvery blanket on them, and all their body heat goes out, reflects off the silvery surface, and then is reflected back to them, and they actually heat up very, very quickly. So radiation can occur in a vacuum. We've got Wien's law to relate the wavelength and the temperature, and radiation can be transmitted. Once it's emitted, once it strikes a surface, it can be absorbed, it can be reflected, or it can be transmitted. Thank you.